We have to develop a relationship. We know that in table A to C, the CP relationship is given against temperature, a specific heat relationship for ideal gases. You know that H is equal to enthalpy is equal to internal energy plus RT. We have seen this in the last slide or the last lecture. And if I integrate this, if I differentiate enthalpy with respect to internal energy, I would have this relationship that dH is equal to du, and R is a constant. I'll have dt. So far, is it clear? The
Yes,
brace.
sir.
All right.
Yes, sir.
Now you know that dH is essentially equal to Cp dt, and du is essentially equal to Cv dt. This is known to you, is it?
Yes, sir.
So if I plug in over here, dH is equals to Cp dt and du is equals to Cv dt, I'll have essentially this equation which says that Cp dt is equals to Cv dt plus R dt. In this equation, the dt would cancel out and you would essentially have an equation which says Cp is equal to Cv plus R. All right.
Yes, sir.
So for ideal gas, you'll have this equation which says is equals to Cv plus R. Now R is the constant which is fixed for the gas. If you know the constant R for the gas and you know the relationship of Cp with temperature, you can find out the relationship for Cv. Clear enough?
Yes, sir.
Good. So this is when you are expressing things in terms of per kg. R, if you remember, is for a specific gas and it is expressed per unit kg. If the same expression is to be expressed in terms of per unit mole, you will have this expression Cp having a dash on top of it, which means the kilojoules per kilomole per Kelvin or per degree centigrade. Similarly for Cv, and Ru is a universal gas constant, which is again per unit kilomole. Clear enough? So you can use either of the
Yes,
two
sir.
relationships. All right. Now, if you have these two relationships and you have the relationship of Cp with temperature, you can find out Cv. We'll have a look at it in an example which is coming in a few minutes time. Another thing is the specific heat ratio. Specific heat ratio is basically defined by the symbol K, and it is the ratio of Cp over Cv. This ratio varies with temperature, but the variation is very little. For monoatomic gases, helium, argon, and etc., this ratio is 1.667, and for diatomic gases, this relationship, which includes air also, is 1.4. So Cp over Cv for monatomic gases is 1.667 and for diatomic gases including air is 1.4. So the Cp of an ideal gas, coming to your question, can be determined if you know the Cv and Cr values. So let's say if Cv is given for air at 300 Kelvin, Cv is given to me, R is known to me, and both are per kgs. So I'll have Cv plus R would give me the Cp value, or if I have per mole value, Cv per unit mole is 20.80 and Ru I know is 8.314 per kilomole. I'll have the per kilomole value of Cp to be the summation of the two values. Is it clear? Tabriz?
Yes, sir. Yes, sir.
Okay.
Clear.
All right. Now we'll look at one of the example which includes all the three methods of calculating del U and del H, and we'll see how we can use the three mechanisms to find out our respective values. It says that air at 300 Kelvin and 200 kilopascal is heated at constant pressure. Now, constant pressure refers to Cp to 600 Kelvin. Determine the change in internal energy. Internal energy, you know, is related to Cv of air per unit mass using number one, the data from the air table, which is assuming air as an ideal gas, A17. The functional form of the specific heat, this is table A2C, where you have a relationship of CPT in terms of A plus BT plus CT minus 1, and so on and so forth, whatever the relationship is. And the average specific heat values, which is table A to B. So all the three mechanisms are being specified. First, we'll look at the mechanism which is table A17, which is for the ideal gas air. Now, you know that these three mechanisms, table A2C and A2B, these are the three mechanisms. The first is table A17. You know that your temperature, initial temperature is 300 Kelvin and your final temperature is 600 Kelvin. So if I have to integrate to find out del U from 300 Kelvin to 600 Kelvin CV temperature dt, I essentially know that from this table, for the value which says 300, it means that the U value, delta U from 0, delta U is equals to from 0 to 300 CVT dt is essentially equal to the U column value against the specific temperature 300, which is 214.07. So this is 214.07, whatever the units. Clear enough? Is this point clear?
Yes, sir.
And delta U is equal to the second temperature is 600. So from 0 to 600 Kelvin, CVT dt is essentially calculated from the remaining portion of the table. Temperature is 600, U value is 434.78. So this is 434.78. If I have to calculate delta U from 300 to 600 CVT dt, this would essentially be the difference between the two values. Is it clear to you? It would be 434.78 minus 214.07. Clear enough? Is this point clear to you?
Yes, sir.
So if I erase all the ink, so this is at 300 Kelvin. This is the value, and at 600 Kelvin, this is my value. And the difference of the two would give me the change in internal energy as my system moved from 300 Kelvin to 600 Kelvin. Clear? Is this point clear how to use the table A17?
Yes, sir. Clear.
All right. Now the second thing is when you have to use the functional form, which is table A2C. So if you go to table A2C, you'll see air as the substance. The relationship is A, B value, C value, and D is given for this temperature range, and it is given the CP relationship is this A plus BT plus CT square plus DT cube. This relationship is given to you. A, B, C, and D values are given to you. And if you see, this value is kilojoules per kilomole per Kelvin. So you remember that Cp per kilomole is essentially equal to Cv per kilomole plus Ru value. This relationship you remember?
Yes, sir.
This is the Cp relationship with regards to temperature. A plus B plus C plus dt. I mean, these three constants are with regards to temperature having the power 1, 2, and 3. This is the constant A. And if I add, if I want to have the relationship for CV temperature, it would essentially be what? Cp molar relationship for temperature minus the Ru value, which is again the constant. So if I these are the constant values. If I do Cp minus Ru, I'll have basically the constant would be instead of A for Cv, this is for Cv, relationship for temperature. The constant instead of having A, I'll have A minus Ru. Sorry. Is it clear to you? How
Yes,
you
sir.
would find out the relationship? So you have the A value given to you have the B value given to you, C value is given to you, D is given to you, Ru you know is 8.314, the universal gas constant. So if you have this relationship and you integrate from T1 to T2, where T1 is 300 Kelvin and T2 is 600 Kelvin, once you do the integration, you will come to know that the change in internal energy per unit kilomole is 6447 kilojoules per kilomole. So far, is it clear?
Yes, sir.
All right. Once you do, you have to find it per unit mass. In table A1, the molar mass of air is given to you as 28.97 kilojoules per kilomole. So if you divide this internal energy by the molar mass, you would essentially have the value of change in internal energy per unit mass, which would be 222.5 kilojoules per kg. The second method is clear?
Yes, sir. Clear.
All right. Now we move on towards the third mechanism, which is taking the average. So my first temperature is T1 is table A to B. We are moving on towards table A to B. A to B. This is my table. The fluid is air. Cp values are given and Cv values are given. Now, if I look at my temperature, the first temperature was 300, was 6. So if I look at the average temperature is 300 Kelvin plus 600 Kelvin divided by 2, which comes out to be 450 Kelvin. If I look at this table, 450 Kelvin is mentioned against these values, and since I am talking, I have to calculate the delta U. Delta U is essentially what? Delta U is integral T1 to T2 Cv temperature dt. Now, if this value is a constant value, I can have this relationship T1 to T2 Cv average dt, and CV average could come out and multiplied by T2 minus T1. This average value is the value at average temperature, which is 0.733. And then I can multiply it by the temperature difference. Is it clear? The third method, is it clear?
Yes, sir.
So the average value at 450 Kelvin is 0.733, and the temperature difference is 600 Kelvin minus 300 Kelvin multiplied by this value would give you the change in internal energy for the air as the ideal gas if it moves from 300 Kelvin to 600 Kelvin. I hope the three methods are clear to you. Let's now look at one more example and try to understand the piston cylinder device contains 0.5 meter cube of nitrogen gas at 400 kilopascal and 27 degrees centigrade. An electrical heater within the device is turned on and is allowed to pass this much amount of current for this much time from a source having the voltage of this much voltage, 120 volts. Nitrogen expands at constant pressure and a heat loss of 200 to 2800 joule occurs during the process. Determine the final temperature of nitrogen. So if we try to have this example over here, this is the example which says nitrogen is your fluid, your pressure is constant, it says constant pressure process. V1, P1 and T1, they are given to you. This is the work electrical into the system, and 2800 joule is the heat that is moving out of the system. So in order to determine the final temperature, You first determine the electrical work into the system, which is VIT. Voltage is given to you, current is given to you, you multiply it by the time in seconds, divided by 1000. This is the electrical work that is being done on the system. If you remember the constant pressure equation, the mass of nitrogen can be determined using the ideal gas equation, which says PV equals to MRT. Pressure is given to you, volume is given to you, temperature is given to you, R value can be found out from the table, and once you find out from the table, you can determine the mass of your system to be 2.245 kgs. Now, if you remember the energy balance equation, the energy balance says that E in minus E out is equal to change in energy of the system. And for a constant pressure process closed system, you have work electrical in minus Q out minus boundary work is equal to delta U. Or if you remember, you have the equation in this form where you have Q minus W equals to delta U, and you divide Q into uh, work other and boundary work equals to delta U. Sorry. Or if you want to have the complete equation, it says Q in plus work in minus Q out plus work out equals to change in delta U if you're having a stationary system. Now there is no Q in, so Q in would be 0. Work in is basically work electrical into the system minus Q out, and work out, we have divided work out into two forms. There is no other work which is being done by the system instead of the boundary work. So you will essentially have, sorry, this is minus, and you will also have minus over here. This is essentially equal to delta U. If you apply this equation, work electrical in is something that you have calculated. If you go back to the slides, work electrical into the system you have calculated. Q out is already given to you. So if you come to the system, work electrical in is known to you, Q out is known to you, and since it says that you are having the boundary work and delta U, you can combine these two into delta H. And delta H can be written as mass multiplied by H2 minus H1. So this is given to you, this is given to you, mass is given to you. H2 minus H1 is of importance, and this delta H for ideal gas, delta H for ideal gas is also written as Cp dt, and Cp dt is what? T2 minus T1. So in this equation, if you know that the Cp value for nitrogen at room temperature, since you are at about room temperature over here, your temperature is 27 degrees centigrade. So you will use the Cp value at room temperature from table A2A, and this is you have calculated, this is given to you. Mass you have calculated, Cp value from table 2A, T1 is given to you. You can find out the final temperature to be 56.7 degrees centigrade. Clear enough?